Before we can speak of black holes, before we can wonder at the darkness that fills our universe, we must first understand the stage upon which these mysteries unfold. And that stage is not empty space, not the void we might imagine when we close our eyes and picture the cosmos. It is something far stranger, far more beautiful. It is the fabric of space-time itself. Imagine, if you will, that you are standing in a quiet room. The floor beneath your feet feels solid, dependable. You drop a pen and it falls. This seems natural. This seems like the way things should be. But why does the pen fall? For thousands of years, humans thought they knew the answer. Objects fall because they seek their natural place. Objects fall because invisible forces pull them downward. But the true answer, the one that Albert Einstein gave us in 1915, is far more elegant, far more strange. The pen falls because you and the pen and the earth beneath you all exist within a geometry that is curved. Space itself and time itself are woven together into a single fabric, and mass, the substance of things, causes this fabric to curve, to dimple, to fold in ways that guide the motion of everything that moves. Let us begin at the beginning, in the way that one might trace a river back to its source. Before Einstein, space was thought to be like an infinite, empty container. Time was thought to flow uniformly, like a great cosmic clock ticking the same seconds for everyone, everywhere. If you were on Earth and I were on a distant star, we would both agree on when something happened, on how much time had passed between two events. Space was the stage, time was the music, and they were separate, independent, unchanging. But then came the experiments. In the late 1800s, physicists began measuring the speed of light with extraordinary precision. They discovered something unsettling. No matter how fast you were moving, no matter whether you were racing toward a beam of light or running away from it, the light always appeared to move at the same speed. Exactly the same speed, approximately 300,000 kilometers per second. This should not have been possible. If you are in a car driving at 60 kilometers per hour and another car passes you going 80 kilometers per hour, you perceive that car as moving 20 kilometers per hour faster than you. This is common sense. This is everyday experience. But light does not obey this rule. Light is always measured at the same speed, regardless of the motion of the measurer. Einstein, working as a patent clerk in Bern, Switzerland, thought deeply about this puzzle. He performed what he called thought experiments, imagining himself riding on a beam of light, imagining clocks and trains and flashes of lightning. And in 1905, he published a paper that changed everything. He proposed that space and time are not separate. They are unified. What one observer perceives as pure space, another observer, moving at a different speed, perceives as a mixture of space and time. If you were to travel very fast, approaching the speed of light, time would slow down for you relative to someone standing still. Your clock would tick more slowly. Your heartbeat would be more languid. And space, in the direction of your motion, would contract, squeezing together like an accordion. This is not an illusion. This is not a trick of perception. This is the actual structure of reality. But this was only the beginning. The 1905 paper, known as special relativity, dealt with objects moving at constant speeds. It did not yet explain gravity. It did not yet explain why the pen falls, why the Earth orbits the Sun, why the Moon tugs at the tides. And so Einstein spent the next 10 years thinking, calculating, wrestling with the mathematics of curved spaces. He realized that gravity is not a force in the way that Newton had imagined. There are no invisible hands pulling objects together. Instead, mass and energy tell space-time how to curve. And the curvature of space-time tells matter how to move. A planet does not orbit a star because the star reaches out and grabs it. A planet orbits a star because the star's mass creates a valley in spacetime, and the planet simply follows the natural contours of that valley, moving along what is called a geodesic, the straightest possible path in a curved space. Imagine a heavy ball placed on a stretched rubber sheet. The sheet sags around the ball, creating a depression. If you roll a marble near the marble will curve around it, spiraling inward or orbiting, depending on its speed. This is not a perfect analogy because the rubber sheet is two-dimensional and space-time is four-dimensional, 3 of space and 1 of time. But it captures something essential. Mass creates curvature. Curvature creates motion. The equations that describe this curvature are called the Einstein field equations. They are 10 interrelated equations, elegant in their symmetry, ferocious in their complexity. On one side of the equal sign is the geometry of spacetime, described by something called the metric tensor, which tells you how distances and durations are measured. On the other side is the distribution of mass and energy, described by the stress-energy tensor. The equations say, here is how much stuff there is, and here is how space bends in response. These equations are difficult to solve. In fact, exact solutions are rare. Most of the time, physicists must make approximations, simplifying the situation by assuming symmetry, assuming that the mass is distributed in a sphere, or a disk, or some other simple shape. But there are a few cases where exact solutions exist, and these solutions are windows into the deep structure of reality. One of the first exact solutions was found by Carl Schwarzschild, a German physicist and astronomer. In 1915, the same year Einstein published his theory of general relativity, Schwarzschild was serving in the German army, stationed on the Eastern Front during the First World War. In between his military duties, in the cold and the mud, he read Einstein's papers and began to work on the equations. He wanted to find the shape of space-time around a perfectly spherical, non-rotating mass. Within weeks, he had an answer. The Schwarzschild solution describes the curvature of space-time outside a spherical object, like a star or a planet. It predicts how clocks will run more slowly in stronger gravitational fields, how light will bend as it passes near massive objects, how orbits will deviate slightly from the perfect ellipses predicted by Newton. But the solution also contains something strange, something that Schwarzschild himself may not have fully understood. It predicted that if you compressed enough mass into a small enough volume, space-time would become so severely curved that it would form a kind of boundary, a point of no return. This boundary is now called the event horizon. Inside the event horizon, the curvature of space-time is so extreme that all paths, all possible trajectories lead inward. There is no way to move outward, no way to escape, not even if you were traveling at the speed of light, because light itself cannot climb out of that gravitational well. At the very center of this region, the equations predict a singularity, a place where the curvature becomes infinite, where the usual rules of physics break down. Schwarzschild sent his solution to Einstein in December of 1915. Einstein was impressed, but skeptical. He thought the singularity was a mathematical artifact, a sign that the equations were being pushed beyond their limits. He believed that nature would find some way to avoid such extremes. For many decades, most physicists agreed. They thought that even if a star collapsed under its own gravity, some force, some pressure would halt the collapse before a singularity could form. Perhaps the matter would find a new equilibrium. Perhaps some unknown quantum effect would prevent the catastrophe. But as the 20th century progressed, as astronomers observed the universe with greater and greater precision, the evidence began to mount that these objects, these black holes, were not just theoretical curiosities, they were real. Before we turn to the question of how black holes form, how stars die and collapse into darkness, let us linger a little longer on the geometry itself. What does it mean for space-time to be curved? What does it feel like if we could somehow experience it directly? Consider two explorers, both floating in space, both initially at rest relative to each other, separated by a small distance. If there is no mass nearby, if space-time is flat, these two explorers will remain at rest relative to each other forever. But if there is a massive object nearby, a planet or a star, the curvature of space-time will cause the two explorers to drift together, not because any force is acting on them, but because the geodesics, the natural paths they follow, are converging. This is called tidal gravity. It is the reason the moon raises tides on Earth. The moon's gravity is slightly stronger on the side of the Earth facing the moon, and slightly weaker on the far side. This difference stretches the Earth, pulls the oceans into an elongated shape. Near a black hole, tidal forces become extreme. If you were to fall feet first toward a black hole, the gravity at your feet would be much stronger than the gravity at your head. You would be stretched vertically, compressed horizontally. This process is sometimes called spaghettification, a whimsical term for a violent and ultimately fatal phenomenon. Your body would be pulled into a long, thin strand, your atoms torn apart by the relentless gradient of gravity. But this would only happen if the black hole were relatively small. If the black hole were very massive, millions or billions of times the mass of the Sun, the event horizon would be very large, and the tidal forces at the horizon would be gentle, almost unnoticeable. You could cross the event horizon without feeling anything unusual. You would not know, in that moment, that you had passed the point of no return. Only later, as you fell deeper, as the curvature grew stronger, would the tidal forces become unbearable. Time itself behaves strangely near a black hole. If you were to hover just outside the event horizon, holding yourself in place with a powerful rocket, and you looked at a clock far away from the black hole, you would see that clock ticking very fast. Hours would pass on the distant clock for every minute on your own. And if someone far away looked at your clock, they would see it ticking very slowly. They would see you moving in slow motion, your words drawn out into a deep, slow rumble. And if you were to fall across the event horizon, sending light signals back to a distant observer as you fell, those signals would become more and more redshifted, stretched to longer and longer wavelengths. The last signal you sent, just as you crossed the horizon, would be stretched infinitely, taking forever to reach the outside universe. To the distant observer, you would appear to slow down, to freeze at the horizon, your image fading and reddening, but never quite disappearing. But from your perspective, nothing special would happen at the horizon. You would simply continue falling into the darkness toward the singularity. This strange asymmetry, this difference between what the falling observer experiences and what the distant observer sees, is one of the deepest puzzles of black hole physics. It is related to the question of information, of what happens to the details of matter that falls into a black hole. A question we will return to later when we have walked further into this landscape of mystery. For now, let us simply appreciate the strangeness of the geometry. Space-time is not a fixed stage. It is dynamic, responsive, alive in a sense. It bends and flexes in response to matter and energy. And when matter is compressed into a small enough volume, when the density becomes high enough, space-time can bend so sharply that it creates a region from which nothing can escape. Not matter, not light, not information. This is the essence of a black hole. This is the geometric fact from which all the strangeness flows. Einstein's equations do not tell us where black holes come from. They do not tell us whether black holes actually exist in nature. They simply say, if you arrange matter in this way, space-time will curve in this way, and the result will be this kind of object. The question of whether nature does arrange matter in that way Whether the universe contains these dark wells is a question for observation, for astronomy, for the patient gathering of evidence. And the evidence, as we will see, is overwhelming. Black holes are not rare. They are not exotic oddities confined to the imaginations of theoretical physicists. They are common features of the universe. There is almost certainly a black hole at the center of every large galaxy, including our own Milky Way. There are probably millions of smaller black holes scattered throughout each galaxy, the remnants of dead stars. And there may be other kinds of black holes as well, primordial black holes formed in the violence of the Big Bang. Tiny black holes that might flicker into existence in particle accelerators, though this last possibility remains speculative. But before we turn to the question of how black holes form, before we describe the death of stars, let us pause and reflect on what we have learned. We have learned that space and time are not separate, that they are woven together. We have learned that this fabric is curved by mass and energy, and that the curvature guides the motion of everything that moves. We have learned that if the curvature becomes extreme, it can create boundaries in space-time, regions from which there is no escape. These are not just abstract mathematical ideas. They are descriptions of the actual universe, confirmed by countless experiments and observations. Clocks on GPS satellites, high above the Earth's surface, do run faster than clocks on the ground, just as Einstein predicted. Light from distant stars does bend as it passes near the Sun, just as the field equations require. And the orbit of Mercury, the innermost planet, does precess in a way that Newton's theory could not explain. But Einstein's theory predicts perfectly. The universe is weirder, more intricate, more beautiful than common sense would suggest. And black holes, these darkest of objects, are among the clearest expressions of that weirdness. They are places where the geometry of space-time becomes so extreme that it defeats intuition, where the rules we learned from everyday experience no longer apply, where we must rely entirely on mathematics and observation to guide us. And so we stand at the threshold, ready to step deeper into the mystery. We have the foundation. We understand, at least in outline, the nature of the stage. Now we can ask, what are black holes made of? How do they form? What happens at their boundaries, at their centers? These questions will occupy us in the sections to come, but for now, rest in the knowledge that space-time is curved, that gravity is geometry, and that the universe is stranger and more wonderful than we ever imagined. Close your eyes, if they are not already closed. Feel the pull of the earth beneath you, the gentle insistence that keeps you grounded. That pull is not a force reaching up to grab you. It is the shape of space-time itself, curved by the mass of the planet, guiding you along the straightest possible path through a geometry that is not flat. You are always falling in a sense, always following the contours of a curved universe. And in that falling, in that surrender to geometry, there is a kind of peace. Let that peace settle over you now as we prepare to journey deeper into the anatomy of darkness itself. We have established the foundation, the curved geometry of space-time. Now we must ask a more direct question, a question that seems simple but conceals great depth. What is a black hole? Not in the abstract sense of geometry and equations, but in the concrete sense of structure and substance. What are black holes made of? The answer is both simple and strange. A black hole is not made of anything, or rather, it is made of the absence of anything we can observe. A black hole is a region of space-time where matter has collapsed so completely that it has disappeared from view, leaving behind only gravity, only curvature, only the geometric scar of its own existence. Let us begin with the most familiar process, the one that creates the black holes we are most certain about. Let us begin with the death of stars. Stars are born in clouds of gas and dust, vast nebulae that span light years of space. Gravity pulls the gas together, slowly at first, then faster as the cloud becomes denser. The center of the cloud heats up as it contracts, the gas molecules colliding more and more frequently, moving faster and faster. Eventually, the temperature and pressure at the center becomes so great that hydrogen atoms begin to fuse together, forming helium and releasing enormous amounts of energy in the process. This energy pushes outward, creating a pressure that balances the inward pull of gravity. The cloud stops collapsing. A star is born. For most of its life, a star exists in this delicate equilibrium. Gravity pulls inward. Pressure from nuclear fusion pushes outward. The two forces balance, and the star shines steadily, converting hydrogen into helium in its core. Our Sun has been in this state for about 4.5 billion years, and will remain so for another 5 billion years or so. But eventually, the hydrogen in the core runs out. The fusion slows, the pressure drops, and gravity begins to win. The core contracts, heating up as it does so. If the star is massive enough, the temperature in the core can become high enough to fuse helium into heavier elements: carbon, oxygen, neon, magnesium. Each new fuel burns faster than the last, releasing less energy per fusion reaction, supporting the star for a shorter and shorter time. For a star much more massive than the Sun, perhaps 10 or 20 or 50 times the Sun's mass, this process continues through a series of shells, each shell fusing different elements. The core becomes like an onion, with layers of iron, silicon, oxygen, carbon, helium, and hydrogen. Each layer burning its fuel, each layer contracting as its fuel is exhausted. And at the very center, iron accumulates. Iron is the end point. Iron cannot be fused into heavier elements in a way that releases energy. Fusing iron requires more energy than it produces, so the iron core grows, becoming denser and denser until it reaches a critical mass. At that point, the core can no longer support itself. The pressure is not enough to resist gravity, and in less than a second, the core collapses. The collapse is catastrophic. The core, which was about the size of the Earth, shrinks to a sphere perhaps 20 kilometers across. The density becomes so great that electrons are forced to merge with protons, forming neutrons. The core becomes a single giant atomic nucleus, held up not by ordinary pressure, but by neutron degeneracy pressure, a quantum mechanical effect that prevents neutrons from being squeezed too closely together. This object is called a neutron star, but the collapse does not stop quietly. The outer layers of the star, still falling inward, crash into the rigid neutron core and bounce. A shock wave forms, blasting outward through the star, ripping it apart. This explosion is called a supernova. For a few weeks, the supernova can shine as brightly as an entire galaxy, releasing in that brief time more energy than the Sun will produce in its entire 10 billion year lifetime. The explosion scatters the outer layers of the star into space, enriching the interstellar medium with heavy elements: carbon and oxygen and iron, the elements that will later form planets and eventually life. But what happens to the core? If the core is less than about 2 or 3 times the mass of the Sun, neutron degeneracy pressure is enough to hold it up. The core becomes a neutron star, a city-sized ball of matter so dense that a teaspoon of it would weigh as much as a mountain. Neutron stars are strange, exotic objects, but they are stable. They do not collapse further. However, if the core is more massive than about 3 solar masses, neutron degeneracy pressure is not enough. Nothing is enough. There is no known force, no known pressure that can prevent the collapse from continuing. The core shrinks past the neutron star stage. It becomes smaller and smaller, denser and denser. And according to Einstein's equations, it will continue to shrink until it forms a singularity, a point of infinite density, zero volume, where the laws of physics as we know them cease to apply. Around this singularity, space-time curves so sharply that an event horizon forms. The event horizon is not a physical surface. It is not made of matter. It is simply a boundary in space-time, the point of no return. Any object that crosses the event horizon, any particle, any photon of light, will be pulled inexorably inward toward the singularity. There is no escape, not because of some physical barrier, but because the structure of space-time itself has been so distorted that all future paths, all possible trajectories lead inward. The size of the event horizon depends on the mass of the black hole. For a non-rotating black hole, the radius of the event horizon is given by a simple formula, the Schwarzschild radius. Slightly. It is equal to twice the gravitational constant times the mass divided by the speed of light squared. For a black hole with the mass of the Sun, the Schwarzschild radius is about 3 kilometers. For a black hole with the mass of the Earth, it would be less than a centimeter. This means that to turn the Sun into a black hole, you would have to compress it into a sphere 6 kilometers across. To turn the Earth into a black hole, you would have to compress it into a sphere smaller than a marble. These are not practical scenarios. There is no known process that could compress the Sun or the Earth in this way. But for the cores of massive stars, already compressed to extraordinary densities by their own gravity, the formation of a black hole is not just possible, it is inevitable. Once the event horizon forms, the black hole is remarkably simple. It has only 3 properties: mass, electric charge, and angular momentum, which is a measure of how fast it is spinning. Everything else, all the details of the matter that formed the black hole, all the information about what kind of atoms it was made of, what shape it had, what its history was, all of that information is lost. This is sometimes called the no-hair theorem, a playful name for a profound result. Black holes have no hair, no distinguishing features beyond mass, charge, and spin. In practice, black holes in nature are almost certainly electrically neutral. If a black hole had a net charge, it would attract opposite charges from the surrounding environment, neutralizing itself very quickly. So we are left with 2 properties, mass and spin. And most black holes, formed from the collapse of rotating stars, are expected to be spinning, sometimes very rapidly. A spinning black hole is described by a different solution to Einstein's equations, found by Roy Kerr in 1963. The Kerr solution is more complex than the Schwarzschild solution. It predicts that a spinning black hole drags space-time around with it, creating a region called the ergosphere, just outside the event horizon. In the ergosphere, space-time itself is rotating, and it is impossible to remain stationary. Even light, trying to hover in place, is dragged around the black hole, forced to move in the direction of the spin. The event horizon of a spinning black hole is not perfectly spherical. It is flattened at the poles and bulges at the equator, like the Earth, but far more extremely. And inside the event horizon, the structure is even stranger. In a Schwarzschild black hole, the singularity is a point at the center. In a Kerr black hole, the singularity is a ring, a circle of infinite density, lying in the equatorial plane. This ring singularity has led to much speculation. Some solutions to the equations suggest that it might be possible to pass through the ring without hitting the singularity, emerging into a different region of space-time, perhaps even a different universe. But these solutions are not considered physically realistic. They require the black hole to be perfectly symmetric, with no perturbations, no irregularities. In the real universe, any black hole will be slightly lumpy, slightly disturbed, and these disturbances are expected to turn the ring singularity into a more chaotic, more destructive region where the classical equations break down entirely. And this brings us to one of the central mysteries of black hole physics. What actually happens at the singularity? Einstein's equations predict that the density and curvature become infinite, but most physicists do not believe that infinities are real. Infinities are a sign that the theory is being pushed beyond its domain of validity, that some new physics, not included in general relativity, must come into play. The new physics is expected to be quantum gravity, a theory that combines general relativity with quantum mechanics. Quantum mechanics is the theory of the very small, the theory that describes atoms and particles. General relativity is the theory of the very large, the theory that describes stars and galaxies. In everyday life, in most astronomical situations, the two theories operate in separate domains. Gravity is important at large scales. Quantum mechanics is important at small scales. But at the singularity of a black hole, both become important at the same time. The density is so high, the volume so small, that quantum effects cannot be ignored. But we do not yet have a complete theory of quantum gravity. We have candidates, approaches like string theory and loop quantum gravity, but none of them have been confirmed by experiment. And so the singularity remains a mystery, a place where our current understanding fails, where the equations produce nonsense, where we must simply admit ignorance. This does not mean black holes are not real. It means that our description of them is incomplete. The event horizon is almost certainly real, a well-defined boundary that can be studied and understood using general relativity. But the singularity, the very heart of the black hole, may be something different from what the classical equations suggest. It may be a region of quantum foam, a place where space-time itself is fluctuating wildly, where the smooth geometry of Einstein's theory gives way to something more fundamental, more discrete, more strange. For the purposes of understanding black holes as astronomical objects, the nature of the singularity is not critical. What matters is the event horizon, the boundary that separates the black hole from the outside universe. And the event horizon, strange as it is something we can study, something we can observe, at least indirectly. Let us now consider what it would be like to approach a black hole, to fall toward the event horizon. Imagine you are in a small spacecraft, far from the black hole, in a region where space-time is nearly flat. You aim your spacecraft toward the black hole and begin to fall. At first, nothing seems unusual. The black hole is invisible, a patch of darkness against the stars. But as you fall closer, you begin to notice strange effects. The stars behind you, in the direction you came from, begin to crowd together, their light blue-shifted to shorter wavelengths. The stars ahead of you, in the direction of the black hole, spread out and redden, their light stretched by the gravitational field. If you look to the side, you see a distorted image of the universe, bent and warped by the curvature of space-time. As you fall closer, the tidal forces begin to grow. If the black hole is small, stellar mass, you will feel the stretching long before you reach the event horizon. Your feet, closer to the black hole, will be pulled harder than your head. The difference in force will grow stronger and stronger until your body is torn apart, stretched into a thin stream of atoms. This is spaghettification, and it is as unpleasant as it sounds. But if the black hole is very large, supermassive, the event horizon is so far from the singularity that the tidal forces at the horizon are gentle. You could cross the event horizon without feeling anything unusual, without even knowing that you had crossed the point of no return. The stars above you would still be visible, though distorted. The spacecraft would still respond normally to your controls. Nothing dramatic would happen. Only later, as you fell deeper, as the curvature grew stronger, would the tidal forces become noticeable. And eventually, as you approach the singularity, the forces would grow without limit, destroying you, destroying the spacecraft, destroying everything. But you would not see the singularity. You would not experience the infinite density. Long before you reached it, you would be reduced to your component atoms, then to subatomic particles, then to something we cannot even name. From the outside, from the perspective of someone watching you fall, the experience is entirely different. They see you approach the event horizon, moving slower and slower, your image redder and redder. They never see you cross the horizon. They see you frozen at the boundary, your light stretched to infinite wavelength, your image fading away over an infinite time. From their perspective, you never actually enter the black hole. You are forever suspended at the edge. This is one of the deep paradoxes of black hole physics. The falling observer crosses the horizon in a finite time by their own clock. The distant observer never sees them cross. Both perspectives are correct, but they seem to contradict each other. The resolution lies in the fact that the two observers are measuring time using different clocks, in regions of spacetime with very different curvatures. There is no universal time, no absolute now. Time is relative, curved, flexible. And this brings us to the question of what happens to the information carried by the falling observer. According to quantum mechanics, information cannot be destroyed. If you know the exact state of a system at one time, you can, in principle, calculate its state at any other time, past or future. Information is preserved. But what happens to the information carried by matter that falls into a black hole? From the outside, the matter disappears behind the event horizon. It seems to be lost. But the black hole itself, as we have seen, has no hair. It is characterized only by its mass, charge, and spin. All the other details, all the information about what kind of matter fell in, seems to be erased. This is called the black hole information paradox, and it has been debated for decades. Some physicists argue that information is indeed lost, that black holes are an exception to the rule of quantum mechanics. Others argue that information is not lost, that it is encoded somehow on the event horizon, or radiated out in subtle correlations in the Hawking radiation, a quantum effect we will discuss later. The paradox remains unresolved. It is a sign that our understanding is incomplete, that black holes are teaching us something deep about the relationship between gravity and quantum mechanics, between space-time and information. But for now, we can set aside the paradox and focus on what we do understand, on the observable structure of black holes, on the event horizon and the region just outside it. Because while we cannot see inside a black hole, we can see the effects it has on its surroundings. We can see matter falling toward the event horizon, heating up, glowing brightly. We can see jets of particles blasting out from the poles of spinning black holes, powered by the rotational energy of the black hole itself. We can detect the gravitational waves emitted when two black holes collide and merge, ripples in space-time that propagate outward at the speed of light. These observations, which we will explore in the next section, have confirmed beyond any doubt that black holes exist. They are not just mathematical curiosities. They are real objects abundant in the universe, shaping the evolution of galaxies, converting matter into energy with astonishing efficiency. They are the darkest objects in the cosmos, and yet, paradoxically, they are among the brightest when viewed in the right way. For now, let us rest in the knowledge that we have traced the anatomy of darkness. We have seen how stars die, how their cores collapse, how event horizons form. We have considered the strangeness of the singularity, the point where our current theories fail. We have imagined what it would be like to fall toward a black hole, to cross the event horizon, to be stretched and torn by tidal forces. And we have confronted the paradoxes, the questions that remain unanswered. What happens to information? What is the nature of the singularity? How do gravity and quantum mechanics fit together? These are not just academic puzzles. They are windows into the deep structure of reality. Hints that the universe is more strange, more subtle, more wonderful than we have yet imagined. Close your eyes now and picture the darkness. Not the absence of light, but a darkness that is active, dynamic, a well in the fabric of space-time. Feel the pull of it, the inexorable geometry that draws everything inward. And know that this darkness is not empty. It is full of mystery, full of questions, full of the promise of understanding yet to come. Rest in that darkness now, as we prepare to turn our attention to the ways we can observe the invisible, the methods we use to detect the undetectable. But for this moment, simply rest and let the quiet geometry of the universe hold you. We have established that black holes are dark, that they emit no light, that their defining characteristic is the impossibility of escape. And yet, we know they exist. We know where they are, how massive they are, how fast they are spinning. We can watch them merge, listen to the space-time ripples they create. How is this possible? How do we observe the invisible? The answer lies in a simple principle. While we cannot see black holes directly, we can see their effects on the matter and light around them. A black hole is like a silent dancer in a crowded room. We cannot see the dancer, but we can watch the other dancers swirl and spin in response to their presence. We can infer the pattern of movement, the rhythm, the force of the unseen partner. Let us begin with the simplest method, the one that astronomers used to find the first black hole candidates in the 1970s. If a black hole is part of a binary system orbiting a normal star, the star's motion will reveal the presence of the dark companion. The star will orbit the common center of mass, wobbling back and forth in a regular pattern. By measuring the speed of this wobble, by watching how the star's light is Doppler shifted, blue shifted when it moves toward us and red shifted when it moves away, astronomers can calculate the mass of the unseen companion. If the mass is too large to be a neutron star, if it exceeds about 3 times the mass of the Sun, and if the companion emits no light of its own, then it is almost certainly a black hole. There is nothing else it could be. No other known object can be so massive and so dark. The first object discovered this way was Cygnus X1, a bright X-ray source in the constellation Cygnus. In 1964, a rocket-borne X-ray detector found a powerful source of X-rays in Cygnus. Over the next several years, astronomers identified the source with a blue supergiant star, designated HDE 226868. The star was wobbling, orbiting something massive every 5.6 days. And that something was emitting intense X-rays. The mass of the unseen companion was estimated to be about 15 times the mass of the Sun. Far too massive to be a neutron star, and it was emitting X-rays, which suggested that matter was falling onto it, heating up as it spiraled inward. The conclusion was unavoidable. Cygnus X1 was a black hole. But where were the X-rays coming from if the black hole itself emits no light? The answer is the accretion disk. As matter from the companion star falls toward the black hole, it does not fall straight in. It has angular momentum, a tendency to orbit, and so the matter spirals inward, forming a disk around the black hole, like water spiraling down a drain. In the accretion disk, particles collide, friction heats the gas, and the temperature rises. Close to the black hole, where the orbital speeds are highest, the gas can reach temperatures of millions of degrees. At such temperatures, the gas emits X-rays, high-energy photons that can be detected by X-ray telescopes in space. The accretion disk glows, even though the black hole itself is dark. The brightness of the disk depends on how much matter is falling in, the accretion rate. If the accretion rate is high, the disk is bright. If the accretion rate is low, the disk is dim. By studying the spectrum of the X-rays, the way the brightness changes over time, astronomers can learn about the properties of the black hole, its mass, its spin, the structure of the space-time around it. Some black holes have accretion disks that are incredibly bright. These are the quasars, the most luminous objects in the universe. A quasar is a supermassive black hole at the center of a galaxy, actively feeding on gas and stars. The accretion disk of a quasar can outshine the entire galaxy, emitting more light than 1 trillion suns, visible across billions of light-years of space. Quasars were first discovered in the 1960s, when radio astronomers found bright point sources that looked like stars but had strange spectra. The spectra were highly redshifted, indicating that the objects were very far away and therefore very luminous. The name quasar comes from quasi-stellar radio source, though we now know that not all quasars are strong radio emitters. For decades, astronomers debated what could power such immense luminosity. Some suggested that quasars were regions of intense star formation, where thousands of massive stars were being born and dying in rapid succession. But the most natural explanation, the one that eventually won out, is that quasars are powered by supermassive black holes, millions or billions of times the mass of the Sun, converting the gravitational energy of infalling matter into light with extraordinary efficiency. The efficiency of this process is remarkable. When matter falls into a black hole, a significant fraction of its rest mass energy can be converted into radiation. For a non-spinning black hole, the efficiency is about 6%. For a maximally spinning black hole, it can be as high as 42%. This is far more efficient than nuclear fusion, which converts less than 1% of mass into energy. This efficiency makes black holes the most powerful engines in the universe. A quasar can emit more energy in a second than the Sun will emit in its entire lifetime. And this energy comes from the smooth, inexorable pull of gravity, from the curvature of space-time around a dark, invisible object. In addition to X-rays and visible light, some black holes produce jets. These are narrow beams of particles, electrons and protons, blasting out from the poles of the black hole at close to the speed of light. The jets can extend for thousands or even millions of light-years, far beyond the galaxy that hosts the black hole. They glow brightly in radio waves and sometimes in X-rays and gamma rays. The mechanism that produces jets is not fully understood. It is believed to involve magnetic fields, twisted and amplified by the swirling motion of the accretion disk and the rotation of the black hole itself. The fields act like a cosmic accelerator, flinging particles outward along the poles where the magnetic field lines converge. The particles stream out, carrying energy and momentum away from the black hole and creating the brilliant, elongated structures we see in radio images. These jets can have dramatic effects on the surrounding environment. They plow into the intergalactic gas, creating shock waves, heating the gas, preventing it from cooling and forming new stars. In this way, supermassive black holes regulate the growth of their host galaxies, a feedback mechanism that is now recognized as crucial to understanding how galaxies evolve over cosmic time. But accretion disks and jets are not the only way we observe black holes. In recent years, a new method has emerged, one that allows us to detect black holes even when they are not actively feeding, even when they are dark and quiet. This method relies on the distortion of light and space-time by the black hole's gravity, an effect called gravitational lensing. When light from a distant star passes near a massive object, the path of the light is bent by the curvature of space-time. This is one of the classic predictions of general relativity, confirmed by observations during a solar eclipse in 1919. If the alignment is just right, if the massive object, the distant star, and the observer are all in a straight line, the light from the star can be focused, magnified, creating a brighter image than would otherwise be possible. For black holes, gravitational lensing can create striking patterns. If a black hole passes in front of a background star, the star's light is bent around the black hole, forming a ring of light called an Einstein ring. If the alignment is not perfect, the ring breaks up into multiple images, arcs of light surrounding the dark mass. By measuring the brightness and position of these images over time, astronomers can infer the mass of the lensing object, even if it emits no light of its own. This technique has been used to detect several isolated black holes, wandering through the galaxy, dark and invisible, except for the subtle distortions they create in the light of distant stars. These observations are difficult, requiring precise measurements of stellar positions over many months or years. But they provide a powerful tool for finding black holes that are not actively accreting matter, black holes that would otherwise remain hidden. And then, in 2015, a new era of black hole astronomy began. On September 14, 2015, the Laser Interferometer Gravitational Wave Observatory, LIGO, detected a signal unlike any that had been seen before. It was a gravitational wave, a ripple in the fabric of spacetime itself, created by the collision and merger of two black holes. Gravitational waves are a direct prediction of general relativity. When massive objects accelerate, they disturb the curvature of spacetime, creating ripples that propagate outward at the speed of light. These ripples are incredibly weak. Even the most violent cosmic events produce gravitational waves that stretch and squeeze space by less than a billionth of a meter. Detecting such tiny distortions requires instruments of extraordinary sensitivity. LIGO consists of two detectors, one in Louisiana and one in Washington state, each shaped like a giant L with arms 4 kilometers long. Laser beams travel up and down the arms, bouncing off mirrors, and the beams are combined to create an interference pattern. If a gravitational wave passes through the detector, it stretches space in one direction and squeezes it in the perpendicular direction, changing the lengths of the arms by a tiny amount. This change alters the interference pattern, creating a signal that can be recorded and analyzed. The signal detected on September 14th lasted only a fraction of a second, but it told a remarkable story. Two black holes, one about 36 times the mass of the Sun and the other about 29 times the mass of the Sun, had been orbiting each other, spiraling inward, getting closer and closer. As they spiraled, they emitted gravitational waves, carrying away energy and angular momentum. The frequency of the waves increased, a rising chirp, as the black holes accelerated, orbiting faster and faster. Finally, they collided and merged, forming a single black hole about 62 times the mass of the Sun. 3 solar masses of energy, the equivalent of the mass of 3 suns, was radiated away as gravitational waves in the final moments of the merger. This is more power than the combined light of all the stars in the observable universe, released in a fraction of a second. But the power was not released as light. It was released as space-time itself, vibrating, rippling, carrying information about the masses and spins of the colliding black holes, the shape of the orbit, the final state of the merged object. And LIGO detected it, measuring the infinitesimal stretching and squeezing of space, confirming once again that Einstein's equations are correct, that black holes exist, that gravitational waves are real. Since that first detection, LIGO and its partner detectors, including Virgo in Italy and Kagra in Japan, have detected dozens of black hole mergers. Some involve black holes much more massive than those in the first event. Some involve black holes of very different masses. And some involve neutron stars colliding with black holes or with each other. Each detection provides new information, new insights into the population of compact objects in the universe, the rates at which they merge, the environments in which they form. Gravitational wave. Astronomy has also allowed us to test general relativity in extreme conditions. The mergers involve velocities close to the speed of light, gravitational fields so strong that space-time is wildly distorted, conditions far beyond anything we can create in a laboratory. And yet, the signals match the predictions of Einstein's equations with extraordinary precision. General relativity passes every test. But perhaps the most striking visual confirmation of black holes came in April 2019, when the Event Horizon Telescope collaboration released the first image of a black hole's shadow. The Event Horizon Telescope is not a single telescope, but a network of radio telescopes scattered across the globe, from Chile to Antarctica to Hawaii. By combining the signals from these telescopes, using a technique called very long baseline interferometry, astronomers created a virtual telescope the size of the Earth, with a resolution sharp enough to see the shadow of a black hole millions of light years away. The target was M87, a giant elliptical galaxy in the Virgo cluster. At the center of M87 is a supermassive black hole, about 6.5 billion times the mass of the Sun. The black hole is surrounded by a bright accretion disk and produces a powerful jet, visible in radio images stretching for thousands of light years. The image released by the Event Horizon Telescope shows a dark region, the shadow of the black hole, surrounded by a bright ring of light from the accretion disk. The shadow is larger than the event horizon itself because light rays that pass close to the black hole are bent, creating a region from which no light can reach us directly. The diameter of the shadow, about 40 billion kilometers, matches the predictions of general relativity for a black hole of this mass. The image is blurry, grainy, a rough sketch rather than a detailed photograph, but it is nonetheless profound. It is the first direct visual evidence of an event horizon, the first image of the boundary between the observable universe and the region from which nothing can escape. It confirms in the most direct way possible that black holes exist, that they are not just theoretical constructs, but real objects, casting real shadows against the light of their accretion disks. In 2022, the Event Horizon Telescope collaboration released a second image, this time of Sagittarius A star, the supermassive black hole at the center of our own Milky Way galaxy. Sagittarius A star is much smaller than the black hole in M87, about 4 million times the mass of the Sun. And it is much closer, only about 26,000 light-years away. But imaging it was more difficult, because the accretion flow around Sagittarius A star changes rapidly, flickering on timescales of minutes, making it challenging to combine the data from different telescopes. The image of Sagittarius A star shows a similar structure, a dark shadow surrounded by a bright ring. The ring is slightly asymmetric, brighter on one side than the other, an effect caused by the rotation of the accretion disk and the Doppler boosting of light from the side of the disk that is moving toward us. The image confirms that our galaxy, like most large galaxies, harbors a supermassive black hole at its center, a dark anchor around which hundreds of billions of stars orbit. These observations, from X-ray binaries to quasars, from gravitational lensing to gravitational waves, from the shadow images of the Event Horizon Telescope, have built an overwhelming case. Black holes are real. They exist in nature. They are abundant. And they are not just passive objects, dark wells in space. They are active, dynamic, shaping their environments, regulating galaxy evolution, converting matter into energy with astonishing efficiency. yet they remain mysterious. We cannot see inside them. We do not know what happens at the singularity. We do not fully understand how jets are produced, how magnetic fields are amplified, how information is preserved. Black holes sit at the intersection of general relativity and quantum mechanics, two theories that are both extraordinarily successful in their own domains, but have not yet been fully reconciled. And black holes are not the only dark mystery in the universe. There is another form of darkness, another invisible presence, one that does not emit light, does not form accretion disks, does not create gravitational waves from collisions. This darkness is spread throughout the universe, filling the space between galaxies, forming an invisible scaffolding on which galaxies themselves are built. It is called dark matter, and it is the subject of the next section of our journey. But for now, rest in the knowledge that we have learned to see the invisible. We have traced the methods astronomers use to detect black holes, from the wobble of stars to the ripple of spacetime, from the glow of accretion disks to the shadows cast against the light of distant matter. We have seen that black holes, despite their darkness, are among the most observable objects in the universe, revealed by the profound effects they have on everything around them. Close your eyes and imagine the ring of light around a shadow, the bright halo of an accretion disk surrounding the dark absence of an event horizon. Picture the gravitational waves, ripples in space-time, carrying the story of a collision across a billion light-years of space. Feel the patience of astronomers, watching stars for years, measuring tiny shifts in position and brightness, piecing together the presence of the invisible. Rest now in the quiet certainty that darkness can be known, that the invisible can be observed, that the universe reveals its secrets to those who watch and listen with care. We turn now from black holes, those concentrated wells of darkness, to a different kind of mystery, a darkness that is diffuse, spread throughout the universe, invisible but undeniable. This is dark matter, and it is one of the deepest puzzles in modern physics. Dark matter does not emit light, it does not absorb light, it does not reflect light. It does not interact with electromagnetic radiation in any way that we have been able to detect. And yet, we know it exists, because we can see its gravitational effects. We can see the way it shapes galaxies, clusters of galaxies, the large-scale structure of the universe itself. The story of dark matter begins in the 1930s with an astronomer named Fritz Zwicky. Zwicky was studying the Coma cluster, a large collection of galaxies about 320 million light-years from Earth. He measured the speeds at which the galaxies were moving, orbiting within the cluster, held together by their mutual gravitational attraction. When he calculated how much mass the cluster should contain, based on the speeds of the galaxies, he found something strange. The galaxies were moving much faster than expected. If the only mass in the cluster was the visible matter, the stars and gas in the galaxies, the cluster should not be able to hold together. The galaxies should be flying apart, escaping into intergalactic space. Zwicky concluded that there must be additional mass in the cluster, mass that he could not see. He called it dark matter. His estimate, based on the observed speeds, was that the cluster contained about 400 times as much dark matter as visible matter. This was a radical proposal, and it was largely ignored for decades. But in the 1970s, another astronomer, Vera Rubin, found similar evidence in a different context. Rubin was studying the rotation of spiral galaxies, measuring how fast stars and gas were orbiting around the galactic centers. According to Newtonian gravity, and according to general relativity in the appropriate limit, the orbital speed should decrease with distance from the center. Most of the mass of a galaxy is concentrated in the center, in the bright bulge of stars. As you move outward into the disk, there is less and less mass pulling you inward, and so the orbital speed should drop. But that is not what Rubin observed. Instead, she found that the orbital speeds remained roughly constant, even far from the galactic center, out in the outer regions of the disk, where there were very few visible stars. This was called the galaxy rotation curve problem, and it was deeply puzzling. The simplest explanation was that galaxies contain much more mass than we can see. This mass is not concentrated in the center. It is spread out in a large halo, extending far beyond the visible disk. The halo is made of dark matter, invisible to telescopes, detectable only through its gravitational pull on the stars and gas. Rubin's observations were meticulous, careful, convincing, and they were confirmed by many other astronomers studying many other galaxies. The rotation curve problem is now recognized as one of the strongest pieces of evidence for dark matter. Nearly every spiral galaxy shows the same pattern: flat rotation curves at large distances, indicating the presence of a massive dark halo. The amount of dark matter is substantial. In a typical spiral galaxy, the dark matter halo contains about 5 to 10 times as much mass as all the visible stars and gas combined. This means that most of the mass in a galaxy is invisible. We are seeing only the bright tip of a much larger, much darker structure. But galaxies are not the only places where dark matter reveals itself. Clusters of galaxies also show strong evidence for dark matter, not just from the speeds of the galaxies, as Zwicky observed, but also from the way they bend light. Massive clusters act as gravitational lenses, distorting the images of background galaxies, creating arcs and multiple images. By measuring the strength of this lensing, astronomers can map the distribution of mass in the cluster, both visible and dark. When such maps are made, they show that the mass is far more extended than the visible light. The clusters are dominated by dark matter, which forms a smooth, diffuse halo. The visible galaxies are like fireflies scattered through a dark forest, their light illuminating only a small fraction of the total mass. One of the most striking examples of this is the Bullet Cluster, a pair of galaxy clusters that collided about 150 million years ago. When the clusters collided, the galaxies, which are mostly empty space, passed through each other largely unscathed. But the hot gas between the galaxies, which makes up most of the visible mass, collided and slowed down, creating a shock wave, a bright region of X-ray emission. Gravitational lensing measurements show that most of the mass in the Bullet Cluster is not where the hot gas is. Clearly. Instead, the mass is where the galaxies are, ahead of the gas, having passed through the collision without slowing down. This is exactly what would be expected if dark matter exists. The dark matter halos of the clusters, being collisionless, pass through each other, while the ordinary matter, in the form of gas, collided and separated. The Bullet Cluster is sometimes called the smoking gun for dark matter. It shows that the mass and the light are in different places, that there is matter we cannot see, matter that interacts only through gravity. It is difficult to explain this observation with modifications to gravity alone. The most natural explanation is that dark matter is real. But what is dark matter made of? This is one of the great open questions in physics. We know what dark matter is not. It is not ordinary matter, not protons and neutrons and electrons, not the stuff that makes up stars and planets and people. We know this because ordinary matter interacts with light, and we can account for all the ordinary matter in the universe through observations of the cosmic microwave background, the primordial light from the Big Bang. The cosmic microwave background is a faint glow of radiation filling the entire sky, left over from a time when the universe was hot and dense, about 380,000 years after the Big Bang. At that time, the universe was a plasma, a soup of protons, electrons, and photons, all interacting constantly. But as the universe expanded and cooled, The protons and electrons combined to form neutral hydrogen atoms, and the photons decoupled, traveling freely through space. These photons, redshifted by the expansion of the universe, are what we detect as the cosmic microwave background. The cosmic microwave background is not perfectly uniform. It has tiny fluctuations, variations in temperature of about 1 part in 100,000. These fluctuations are the seeds of all the structure we see in the universe today. The galaxies, clusters, superclusters. They are the imprint of quantum fluctuations from the very early universe, stretched to cosmic scales by the inflationary expansion. By studying the pattern of these fluctuations, cosmologists can infer the composition of the universe. They can determine how much of the universe is made of ordinary matter, how much is dark matter, and how much is dark energy, a mysterious component that drives the accelerated expansion of the universe. The results are striking. Ordinary matter, the atoms that make up everything we see, makes up only about 5% of the total energy density of the universe. Dark matter makes up about 27%, and dark energy makes up the remaining 68%. So dark matter is not ordinary matter. It is something else, some new kind of particle or particles that have not yet been detected in laboratory experiments. Many candidates have been proposed. One of the most popular is called weakly interacting massive particles, or WIMPs. WIMPs are hypothetical particles that interact through gravity and through the weak nuclear force, the force responsible for certain kinds of radioactive decay, but not through electromagnetism. If WIMPs exist, they would have been produced in the hot early universe. As the universe cooled, most WIMPs would have annihilated with their antiparticles, producing radiation. But a small fraction would have survived, and these survivors would make up the dark matter we observe today. The predicted abundance of WIMPs, based on particle physics calculations, matches the observed abundance of dark matter remarkably well, which is one reason WIMPs have been considered a leading candidate for many years. Physicists have built extremely sensitive detectors deep underground, shielded from cosmic rays, hoping to catch the rare interaction of a WIMP with an ordinary atom. These experiments have been running for decades, with ever-increasing sensitivity. But so far, no confirmed detection has been made. The absence of a signal has ruled out many models of WIMPs, though some possibilities remain. Another candidate is called axions. Axions are much lighter than WIMPs, and they interact even more weakly with ordinary matter. They were originally proposed to solve a problem in quantum chromodynamics, the theory of the strong nuclear force, but they also happen to be good dark matter candidates. Axions could be produced in the early universe in large numbers, and they would be stable, long-lived, filling space with a cold, diffuse sea of particles. Detecting axions requires different techniques than detecting WIMPs. Axions can convert into photons in the presence of a strong magnetic field, and experiments are being built to look for this conversion. Some of these experiments, like ADMX in the United States, have been running for years, searching for the faint radio signals that would indicate the presence of axions. So far, no definitive signal has been found, but the search continues. There are other, more exotic possibilities. Some theories suggest that dark matter could be made of primordial black holes, formed in the very early universe, long before the first stars. These black holes would be very small, much smaller than stellar mass black holes, and they would be extremely difficult to detect. Observations of gravitational lensing and other effects have placed strong constraints on the abundance of primordial black holes, ruling out many mass ranges, but some possibilities remain. Another idea is that dark matter is not made of particles at all, but is instead a manifestation of modifications to gravity. Perhaps Einstein's equations are not quite correct at very large scales, and what we interpret as dark matter is actually a deviation from general relativity. Many such theories have been proposed, with names like MOND for modified Newtonian dynamics, or TeVeS for tensor vector scalar gravity. But these modified gravity theories face significant challenges. They must explain not just galaxy rotation curves, but also the bullet cluster, the cosmic microwave background, the large-scale structure of the universe. And most of them struggle to fit all the data. The simplest explanation, the one that fits the observations most naturally, is that dark matter is real, that it is made of some new kind of particle, and that we have not yet detected it because it interacts so weakly with ordinary matter. The search for dark matter is one of the most active areas of research in physics. Experiments are being conducted deep underground, in space, at particle accelerators like the Large Hadron Collider. Theoretical physicists are developing new models, predicting new kinds of particles, new signatures that might be detected. Astronomers are mapping the distribution of dark matter in the universe, using gravitational lensing, galaxy surveys, and simulations. And slowly, the picture is becoming clearer. Dark matter is not uniformly distributed. It forms structures, halos around galaxies, filaments connecting clusters, a vast cosmic web that fills the universe. Ordinary matter, the atoms that make up stars and planets, falls into the gravitational wells created by dark matter, accumulating in the densest regions, forming galaxies and clusters. Computer simulations of structure formation, starting from the tiny fluctuations in the cosmic microwave background and evolving forward in time, show that dark matter is essential. Without dark matter, the fluctuations would not grow fast enough, galaxies would not form, or they would form much later, in a universe very different from the one we observe. Dark matter is the scaffolding, the framework on which the visible universe is built. But dark matter remains invisible. We cannot see it, cannot touch it, cannot detect it directly, at least not yet. We know it only through its gravitational effects, through the way it shapes the motion of galaxies, the bending of light, the pattern of fluctuations in the cosmic microwave background. In this sense, dark matter is like the wind. You cannot see the wind itself, you can only see its effects. The swaying of trees, ripples on water, the movement of clouds. But you do not doubt that the wind exists. You feel it on your skin, you see its consequences, and you infer its presence and its properties. Dark matter is the same. We feel its gravitational tug, we see the consequences in the motion of galaxies, and we infer that it exists, that it is real, that it makes up most of the matter in the universe. And the search to understand it, to detect it directly, to identify what it is made of, continues. This search is not just about satisfying curiosity. Understanding dark matter is essential to understanding the universe. It affects the formation of galaxies, the distribution of matter on the largest scales, the fate of the cosmos itself. If dark matter is made of particles, detecting those particles would be one of the greatest discoveries in the history of physics, opening up a new realm of nature, revealing new forces, new symmetries, new principles. And perhaps, one day, we will detect it. Perhaps a detector deep underground will register the unmistakable signal of a dark matter particle colliding with an atomic nucleus. Perhaps a telescope will detect the faint glow of dark matter particles annihilating in the center of a galaxy, producing gamma rays or other radiation. Perhaps the Large Hadron Collider will create dark matter particles in high-energy collisions, and we will see the telltale signs of missing energy, particles escaping undetected into the darkness. Or perhaps dark matter will remain elusive. Perhaps it interacts so weakly with ordinary matter that we will never detect it directly, and we will have to content ourselves with studying its gravitational effects, mapping its distribution, inferring its properties indirectly. But even this would be progress. Even this would deepen our understanding of the universe, revealing the hidden structures, the invisible architecture that shapes everything we see. For now, dark matter remains a mystery. It is the silent presence, the invisible majority, the dark foundation of the cosmic web. And it reminds us that the universe is not just what we can see. Most of it is hidden, most of it is dark, most of it is unknown. This is humbling, but it is also thrilling. It means there is more to discover, more to understand, more to explore. The darkness is not empty. It is full of matter, full of structure, full of questions waiting to be answered. Close your eyes now and picture the cosmic web, the vast network of dark matter filaments stretching across the universe, connecting galaxies and clusters, forming a skeleton on which the visible universe hangs. Imagine the dark, matter particles, whatever they are, streaming through space, passing through the Earth, passing through your body, undetected, unfelt, but ever present, shaping the universe at the largest scales. Feel the weight of this invisible presence, not as a burden, but as a reminder of how much we have yet to learn. Rest in the knowledge that the universe is vast, that most of it is hidden, and that the search to understand it, to bring the darkness into the light, is one of the noblest endeavors of the human mind. Rest now as we prepare to turn to the deepest questions, the philosophical horizons where black holes and dark matter meet, where physics touches on the nature of knowledge itself. We have journeyed through the geometry of spacetime, traced the anatomy of black holes, observed the invisible through gravitational waves and shadows, and contemplated the silent presence of dark matter. Now, as our exploration draws toward its close, we turn to questions of a different kind. Not questions of observation or calculation, but questions of meaning, of interpretation, of what these dark mysteries teach us about the nature of reality itself. Black holes and dark matter sit at the boundary of the known and the unknown. They challenge our intuitions, force us to confront the limits of our theories, and remind us that the universe is not obliged to make sense to us, not obliged to conform to our everyday experience. In this final section, we will explore some of the philosophical questions raised by these objects. Questions about information, time, knowledge, and the relationship between observer and observed. Let us begin with the question of information, one of the deepest puzzles in black hole physics. We have already touched on this, but it is worth exploring more carefully because it reveals a fundamental tension between two of our most successful theories, general relativity and quantum mechanics. In quantum mechanics, information is never destroyed. This is not an assumption, but a consequence of the way quantum theory is structured. The state of a quantum system at one time determines its state at all future times. The evolution is deterministic, governed by the Schrödinger equation. If you know the quantum state now, you can, in principle, calculate what it was in the past and what it will be in the future. This principle is called unitarity. It means that the total information content of the universe is conserved. Information can be scrambled, spread out, made difficult to access, but it cannot be truly lost. Burning a book seems to destroy information, but in principle, if you could track every atom, every photon of light, every particle of smoke, you could reconstruct the book's contents from the ashes and the radiation. The information is still there, just encoded in a very complicated way. But what happens when you throw the book into a black hole? The book crosses the event horizon and falls toward the singularity. From the outside, it disappears. And the black hole, as we have seen, has no hair. It is characterized only by mass, charge, and spin. All the detailed information about the book, what it said, what language it was written in, what kind of paper it was printed on, all of that seems to be erased. This would seem to violate unitarity. Information has been destroyed, or at least hidden in a way that makes it impossible to recover, even in principle. And this is the information paradox. Does the information survive, encoded somehow on the event horizon or in the Hawking radiation? Or is it genuinely lost? meaning that black holes are an exception to the rules of quantum mechanics. Stephen Hawking, in the 1970s, made the paradox even sharper by showing that black holes are not entirely black. They emit radiation, now called Hawking radiation, through a quantum mechanical process involving particle creation near the event horizon. This radiation is thermal, random, carrying no information about what fell into the black hole. If Hawking was right, then as the black hole evaporates, radiating away its mass, the information that fell in is lost forever. Hawking himself believed this for many years. He argued that general relativity and quantum mechanics were fundamentally incompatible at the singularity, and that information loss was real. But other physicists, including Gerard 't Hooft and Leonard Susskind, argued that information must be conserved, that the paradox was a sign that our understanding of black holes was incomplete, not that quantum mechanics was wrong. The debate continued for decades, and in 2004, Hawking conceded. He announced at a conference in Dublin that he had changed his mind, that he now believed information was preserved after all. He proposed that the information was not lost inside the black hole, but was instead encoded in subtle correlations in the Hawking radiation, in a way that could, in principle, be decoded. But how this encoding works, how the information gets out, is still not fully understood. Some physicists think the answer lies in the holographic principle, the idea that all the information in a volume of space can be encoded on its boundary, like a hologram. In this view, the event horizon of a black hole is like a holographic screen, storing all the information about what fell in. Others think the answer involves quantum entanglement, the strange quantum correlation between particles. They propose that particles falling into a black hole remain entangled with particles in the Hawking radiation, and that this entanglement preserves the information, even if the fallen particles themselves are lost. These ideas are still speculative, still being worked out, but they represent serious attempts to resolve the paradox without abandoning either general relativity or quantum mechanics. The information paradox is not just a technical puzzle. It is a question about the fundamental nature of reality. Does information, the precise details of what exists, have a permanent status in the universe, or can it be truly destroyed? And if it can be destroyed, what does that say about the determinism of physics, the idea that the future is in principle predictable from the present? These are deep questions, and black holes force us to confront them. They are laboratories for extreme physics, places where our theories are pushed to their limits, where the answers we get challenge our assumptions about how the world works. Another philosophical question raised by black holes concerns the nature of time. We are accustomed to thinking of time as universal, as flowing at the same rate for everyone. But general relativity tells us that time is relative, that it depends on the gravitational field, on the curvature of spacetime. Near a black hole, time behaves in ways that defy common sense. Consider again the observer falling into a black hole and the distant observer watching from far away. The falling observer experiences time normally. Their watch ticks at the usual rate. They cross the event horizon in a finite amount of time, measured by their own clock. From their perspective, nothing special happens at the horizon. It is just another point in space, no different from any other, at least locally. But the distant observer never sees them cross. They see the falling observer slow down, approach the horizon asymptotically, their image redder and dimmer, taking an infinite amount of time, measured by the distant clock, to reach the boundary. Which perspective is correct? The answer is that both are correct. Time is not absolute. There is no universal clock that determines when the crossing happens. Each observer has their own time, their own sequence of events, and these sequences do not agree. This is related to the concept of the light cone. At any point in spacetime, you can imagine all the possible paths that light could take, radiating outward. These paths form a cone, the future light cone, representing all the events that can be influenced by what happens at that point. Similarly, there is a past light cone, representing all the events that could have influenced what happens at that point. For an observer far from a black hole, the event horizon is always in the future light cone. It is always something that might happen, but never something that has happened. The distant observer can never confirm that the falling observer has crossed, because the light signals from the crossing never reach them. The horizon is a boundary not just in space, but in time, separating past from future in a way that depends on the observer. This raises a profound question about the reality of events. If an event is never observable to a particular observer, does it happen for that observer? Does the event horizon exist for the distant observer, or only for the falling observer? There is no easy answer. The question touches on the interpretation of general relativity, on the relationship between observation and reality, on the nature of existence itself. Some physicists adopt a perspective called complementarity. They argue that the falling observer's description and the distant observer's description are both valid, but they apply to different domains, different perspectives, and should not be forced into a single, unified picture. This is similar to the complementarity in quantum mechanics, where a particle can be described as a wave or as a particle, depending on what kind of measurement you make, but you cannot describe it as both at the same time. Others find complementarity unsatisfying. They want a single, objective description of what happens, independent of the observer. But black holes may not permit such a description. They may be telling us that reality is fundamentally observer-dependent, that the universe does not have a God's-eye view, a perspective from which all events are unambiguously ordered in time. This is a disorienting idea. It challenges the notion of objective reality, the idea that there is a single true state of affairs, independent of who is observing it. But it is consistent with the spirit of relativity, which tells us that there is no absolute space, no absolute time, no privileged reference frame. And then there is the singularity. We have mentioned it several times, this point or ring of infinite density and curvature at the center of a black hole. The singularity is where general relativity breaks down, where the equations produce infinities, where the classical description fails. Most physicists believe that the singularity is not a real physical object, but a signal that we need a new theory. Just as Newtonian gravity breaks down near the event horizon and must be replaced by general relativity breaks down at the singularity and must be replaced by quantum gravity. The singularity is a placeholder for our ignorance, a reminder that our current understanding is incomplete. But what might replace the singularity? In some approaches to quantum gravity, like loop quantum gravity, the singularity is replaced by a region of extremely high but finite density, where quantum effects prevent the collapse from continuing all the way to a point. In other approaches, like string theory, the singularity might be a place where the extra dimensions of spacetime become important, where the usual notions of distance and time break down, but in a way that is still governed by well-defined equations. These ideas are speculative, untested. We have no direct way to probe the singularity, no way to send a signal out from inside the event horizon to tell us what is really there. And so the singularity remains a mystery, a question mark at the heart of some of the most extreme objects in the universe. But perhaps there is a kind of beauty in this mystery. Perhaps it is fitting that the universe contains regions we cannot fully understand, places where our theories fail, where we must admit the limits of our knowledge. This humility, this recognition of what we do not know, is as important as the knowledge we have gained. And this brings us to dark matter. Dark matter, unlike black holes, does not raise paradoxes about information or time. It is, in many ways, a simpler mystery. We do not know what it is, but we know it exists, and we know how it behaves, at least gravitationally. But dark matter teaches us something important about the nature of scientific knowledge. It teaches us that absence of evidence is not evidence of absence. We cannot see dark matter, cannot detect it directly, at least not yet. But the indirect evidence is overwhelming. The rotation curves of galaxies, the dynamics of galaxy clusters, the patterns in the cosmic microwave background, the large-scale structure of the universe, all of these point to the same conclusion. Dark matter is real. This is how science works. We do not require direct observation to establish the existence of something. We infer existence from effects, from patterns, from the consistency of multiple lines of evidence. We observe the consequences and reason backward to the cause. In this sense, dark matter is like many other entities in science that were inferred before they were directly observed. Atoms were inferred from the behavior of gases and chemical reactions long before they were imaged. Bacteria were inferred from patterns of disease before they were seen under a microscope. The planet Neptune was inferred from perturbations in the orbit of Uranus before it was observed through a telescope. Dark matter fits this pattern. It is an inference, a hypothesis, a placeholder for something we do not yet fully understand. But it is a well-supported inference, consistent with a vast array of observations, and it has successfully predicted phenomena that were later confirmed. And the search continues. The search for direct detection, for a signal in a deep underground detector, for a flash of gamma rays from the annihilation of dark matter particles, for a new particle at the Large Hadron Collider. Each negative result narrows the possibilities, rules out certain models, guides the development of new theories. This is the process of science. It is not a straight path to truth, but a winding journey, with false starts and dead ends, with revisions and refinements. Each experiment, each observation, each calculation brings us a little closer to understanding. And even when we do not find what we are looking for, we learn something valuable. We learn what dark matter is not, and this constrains what it could be. There is a parallel here to the search for quantum gravity. We do not yet have a complete theory that unifies general relativity and quantum mechanics. But we have many ideas, many approaches, many mathematical structures that might, one day, lead to the answer. And each idea, even if it ultimately fails, teaches us something, reveals some aspect of the problem, suggests new directions to explore. This is the nature of fundamental research. It is not always clear where it will lead, what the applications will be, whether the effort will be rewarded. But the pursuit itself is worthwhile because it expands the boundary of the known, because it satisfies a deep human curiosity about the nature of reality, because it reminds us that the universe is vast and strange and full of wonders. And there is comfort in this. Comfort in knowing that we do not have all the answers, that there are still mysteries to solve, questions to ask, frontiers to explore. The darkness, whether it is the darkness of a black hole or the darkness of dark matter, is not something to fear. It is something to study, to probe, to understand, because the darkness is not empty. It is full of structure, full of information, full of patterns waiting to be discerned. The event horizon of a black hole is a boundary, yes, but it is also a surface that encodes information, that tells us about the black hole's history, that connects the inside to the outside in ways we are only beginning to understand. And dark matter, invisible though it is the scaffolding of the universe. It shapes galaxies, guides the formation of structure, determines the fate of the cosmos. Without dark matter, the universe would be a very different place. Stars might not form, or they might form in different ways, in different locations. Galaxies might not exist at all. We might not exist. So the darkness is not a void. It is a presence, a force, a foundation. And understanding it is essential to understanding ourselves. our place in the universe, the story of how we came to be. This brings us to the question of meaning. Does the universe have meaning? Does it have purpose? These are not scientific questions, in the sense that they cannot be answered by experiment or observation, but they are questions that science can inform, that the study of black holes and dark matter can illuminate. The universe, as revealed by modern physics, is governed by laws. These laws are mathematical, precise, predictable. They do not care about us, do not have preferences, do not assign value to one outcome over another. The universe is indifferent. But within this indifference, there is beauty. There is the beauty of symmetry, of simplicity, of the way complex phenomena can be described by a few fundamental equations. There is the beauty of structure, of the way galaxies form and evolve, of the way spacetime curves and flows. There is the beauty of discovery, of the moment when a pattern clicks into place, when a mystery is solved, when the darkness yields to understanding. And there is meaning in the search itself, meaning in the effort to understand, to push the boundaries of knowledge, to confront the unknown with curiosity and rigor. Meaning in the collaboration, the community of scientists and thinkers working together across generations, across cultures, to build a picture of the universe. This meaning is not given to us by the universe. It is something we create through our choices, our values, our commitment to seeking truth. The universe does not need us to understand it, but we are part of the universe, and our understanding is one of the ways the universe comes to know itself. This is a kind of cosmic perspective, a recognition that we are small, temporary, fragile, but also connected, part of a vast web of matter and energy and information that stretches across space and time. Black holes and dark matter remind us of this perspective. They remind us that the universe is larger than we can imagine, stranger than we can conceive, full of mysteries that may take centuries to unravel. But they also remind us of what we can achieve. We have detected gravitational waves, ripples in space-time itself, predicted by Einstein 100 years ago, but thought to be undetectable. We have imaged the shadow of a black hole, a feat that required coordinating telescopes across the entire planet. We have mapped the distribution of dark matter across the universe using observations of light that has traveled for billions of years. These are extraordinary accomplishments. They are testament to human ingenuity, to our ability to work together, to build instruments of astonishing precision, to develop mathematical tools that allow us to describe the universe with accuracy and elegance. And they are just the beginning. There is so much more to learn, so many questions yet to answer, so many mysteries waiting in the darkness. And so we return at the end of our journey to the beginning, to the curved fabric of space-time, to the wells and valleys created by mass and energy, to the boundaries from which nothing can escape, to the invisible presence that shapes galaxies and clusters. We have traveled through the anatomy of darkness, observed the invisible, contemplated the silent presence, explored the philosophical horizons. And we have found that darkness is not the enemy of knowledge. It is the invitation. It is the space where discovery happens, where understanding deepens, where the human mind reaches out to touch the edges of reality. So rest now in the quiet knowledge that the universe is vast, that most of it is hidden, but that the hidden can be known. Rest in the beauty of the equations, the elegance of the theories, the patience of the observers, the ingenuity of the experimenters. Rest in the darkness, not as a place of fear, but as a place of possibility. Know that the black holes are there, at the centers of galaxies, in the remnants of dead stars, bending space-time, creating horizons, teaching us about the limits of our theories. Know that dark matter is there, filling the space between galaxies, forming the cosmic web, holding everything together with its gentle, invisible gravity. And know that we are here, small but curious, temporary but persistent, seeking to understand. Let the darkness hold you now. Let it be a comfort, not a threat. Let it remind you that there is always more to learn, always more to discover, always more to wonder at. Close your eyes and feel the fabric of space-time beneath you, curved by the mass of the Earth, by the sun, by the galaxy, by the universe itself. Feel the pull of gravity, the gentle insistence that keeps you grounded, that guides the motion of planets and stars, that shapes the very structure of the cosmos. And know that this pull, this curvature, is not separate from you. You are part of it, woven into the same fabric, made of the same atoms, governed by the same laws. The universe is not something distant, something separate. It is here, now, in you and around you. Rest in that knowledge. Rest in the mystery. Rest in the darkness. And let yourself drift into sleep, into dreams, into the quiet spaces where understanding and wonder meet, where the boundaries between self and cosmos dissolve, where all is one and one is all. Sleep now, traveler. Sleep in the knowledge that the universe holds you, that the darkness is full of light, that the mysteries are not obstacles but gifts. Sleep and let the gentle geometry of space-time carry you through the night, into the morning, into the future, into the endless, beautiful, unknowable expanse of all that is. Good night. Rest well, and dream of black holes and dark matter and the infinite, magnificent darkness that is the universe itself.